Hello all, I'm Reet and it is my pleasure to present our paper titled Vertex Reordering for Real-World Graphs and Applications and Empirical Evaluation. Let's dive into it by prefacing this talk with what vertex reordering is. Given a graph G with vertex set V and edge set E, we identify vertices by indexing them from 1 to n. Then a vertex ordering pi of V becomes a one-to-one mapping of the vertices to any linear order of 1 to n. We have an input ordering. Why do we need to reorder the vertices? What is the objective? Well, the goal is to preserve the neighborhood properties of a graph. In other words, we want vertices which are closer to each other in a graph to have labels that reflect that closeness. The candidate ordering figure that we have on the right from the point of view of vertex 1, which is shown in red, we can see the other vertices being colored in a way where the more far apart they are from vertex 1, the redness starts fading and becomes more and more blue. For example, vertex 2 and 4 are orange because they are close to 1, while 7 is blue since it is one of the farthest from 1. What reordering has done is that the vertex labels now reflect that closeness, which was not there in the input ordering. How do we formalize these neighborhood properties? We define gap measures. We define the linear arrangement gap between any two vertices I and j as the absolute difference in the ranks in the ordering pi. So the average gap profile of a given ordering for an input graph becomes the average linear arrangement gap over all the edges of that graph. A good reordering is one which minimizes the average linear gap. Here's how we define the graph bandwidth. For any two pair of vertices I and j in the graph such that they are adjacent to each other, the maximum separation between their ranks in the vertex array is the graph bandwidth. This is an example just to show how ordering can affect the metrics I just described. The graph on the left is the original one with the linear arrangement gaps written over the edges. The reordered graph is the one on the right, where you can see the gap values have changed as a result. The average gap has reduced from 3.3 to 1.7, and the bandwidth from 5 to 3. We take a look at different reordering schemes that are in practice and classify them based on the methods or the methodology and the purpose. Gap-based methods directly try to optimize the gap measures using algorithms like simulated annealing, which obviously does not scale. The degree-based ones take into account the degree of the vertices as a feature to come up with an ordering. G-order is a window-based approach which slides a window over the vertex array and optimizes for a score that takes into account the neighborhood and sibling relationships among the vertex pairs in that window. Partition-based ones are actually graph partitioning or community detection tools which have been repurposed to generate an ordering. While the fill-reducing ones have the objective of generating an ordering that tries to concentrate the non-zeros in the adjacency matrix of a graph near the diagonal of that matrix. Part of our objective of this work is to compare a representative subset of these schemes based on their ability to optimize for gap measures. For that, we use 25 real-world graphs as input across 11 reordering schemes, and their quality is judged based on the gap measures described. And here are the results. The way to interpret this plot is that the y-axis shows a fraction of 25 input data set, while the x-axis shows the factor by which one scheme fares, how one scheme fares with respect to the best. For example, G-order, shown as the second solid blue line, does 5 times worse than the best, which is metis, shown in dashed red with triangle markers on 50% of the data sets. The takeaway here is that partition-based schemes shown in red, like rabbit order, metis, etc., do much better than others in minimizing the average gap profile. The next result shows RCM, which is the reverse Cuthell-McKee algorithm, outperforming others when the objective is to optimize for graph bandwidth. We also take a look at the distribution of gaps in input graphs and what the distribution profile looks like for different reordering schemes. For this, we used violin plots, and here are the results. For 3 of the input graphs, which produce quite a varied profile across the orderings. The observations here are that the distributions, as we can see, are multimodal in nature, and the long tails are characteristics of log normal distribution, which show the skewedness in gap distribution. So visually speaking, a good reordering scheme would be one which has a bottom heavy distribution. Moving on to real world application study, prior works on ordering have predominantly focused on a standard suite of applications like PageRank, single source, shortest paths, betweenness centrality, etc. The prototypical end applications that we take a look at are community detection and influence maximization. Our choice of end application is motivated by the fact that these represent more advanced and complex graph operations that feature in several large-scale scientific pipelines. Furthermore, they also encapsulate 2 different types of algorithms. Community detection represents the classic multi-level iterative graph algorithms, while on the other hand, influence maximization implementations entail running stochastic VFSs over the graph to collect samples. For this study, we use 9 large real-world graphs across 5 representative schemes and gauge their impact on the performance of community detection tool Grappolo and influence maximization tool Ripples. In the results, we take a look at memory latency, which is measured as the average latency of loads to memory in cycles. We also take a look at memory hierarchy boundedness, which shows us at which memory hierarchy level was the machine stalled while waiting on data. First, let's take a look at the results from community detection. We present the results as a heat map, where redder is better. The first table shows the time taken to complete the first phase of Grappolo. We consider only the first phase because the subsequent phases analyzes a derivative compressed graph, which has little to do with the input ordering. The iteration heat map shows time per iteration, and the next one shows the iteration count inside the phase. The fourth one shows the final modularity scores. Then the work percentage shows the time the CPU spent in useful non-synchronization work. It is essentially a measure of parallel efficiency. So higher values indicate lesser load imbalance. The final one shows the average work per graph edge. We observe that Grappolo ordering outperforms others in general as far as phase and iteration times are concerned. For example, it outperforms degree sort by a factor of around 2 to 4. As far as parallel efficiency is concerned, Grappolo ordering usually has the highest, while also having the lowest work per edge, which is indicative of better load balancing. Now, while looking at memory latency and boundedness, we go in with the expectation that the lower memory latency should correspond to boundedness at lower cache levels, and lower iteration time should correlate to lower memory latency. But that's not the case. Grappolo ordering tends to be more DRAM bound, even though we were expecting it to be more L1 or L2 bound. We believe that the graph traversal cost may not be the dominant factor in an algorithm's execution time. The algorithm's use of auxiliary data structures, here it is a C++ map that contains the community structure, can result in additional memory accesses that negates the effect of ordering. We now turn our attention to influence maximization, more specifically the state of the art, which is called ripples. A way to judge performance would be to look at the throughput of the algorithm's sampling procedure, which is the hot routine of the implementation, and the corresponding execution time. But we'll get to that. First, we take a look at the memory boundedness results for the largest graph for which this analysis was possible, which is the skitter graph. The expectation was that the runtime profile would be more cache bound as a result of reordering, which would reflect in the throughput and execution time. But again, that is not the case. For example, if you see here, Grappolo and degree sort both are more L1 bound, which would mean more red cells towards the lower end of the profile. But when we look at the throughput and execution time for these two orderings, so the top one is execution time while the bottom one is the sampling throughput. And we look at the highlighted row, which corresponds to the scatter graph. We see that Grappolo and degree sort are on the opposite ends of the spectrum. We hypothesize that this is due to parallel threads competing for memory bandwidth and cache space. Solution. So despite what looks like a modest role that reordering plays in the influence maximization application, we posit that one will see the benefit of reordering if the underlying implementation is made locality aware. Finally, to summarize, we see that partition-based schemes do better optimizing for average gap profile. RCM does best if we want to reduce the graph bandwidth. And reordering has more benefits when community detection is the end application than when it is influence maximization. Finally, does reordering matter? Yes, definitely. It shows us how the end application will use the memory hierarchy. Is reordering worth it? Well, if we use the input graph enough times to amortize the cost of reordering, then definitely yes. This brings us to the end of our presentation. Thank you for listening.